Okay, so good morning, everybody. I'm from the UPC, the Universitat Politècnica de Catalunya, but also from the Institut de Ciències del Mar. And my talk is about underwater target localization. Okay, so the main idea is to how we localize underwater targets, because as my colleague said before, in the lab we can use the GPS very easily, and we can access to the localization of different targets that we want. But in underwater, we don't have access to the GPS because the water attenuates electromagnetic waves. So we need to use other kind of methodologies. And things that we want to localize underwater can be vehicles or marine species that we put some kind of electronic device attached to the species in order to localize them, as I will explain. So at the beginning, the first or one of the first methods that appears in order to localize underwater targets was called long baseline system, which basically was an array of transponders deployed on the seabed, and those transponders could listen for acoustic noise or could transmit information from the transponders to the target that we want to localize and compute the time of flight or time difference of arrival in order to try to triangulate the position of the target. But this is quite expensive in the deployment, because we need to deploy all the receiver in a well-located places. And this is very hard if you want to track things in the deep sea. And also it's difficult to move, because if we spend a lot of time and resources to deploy this network, the network is there and we cannot move into another place. So we can only monitorize the area where we deploy the transceivers. Later on, there appeared other technology, which is called ultra-short baseline system. And basically, the main idea here is that we have different transponders or different active elements together into a single device. So this device in the active sensor is an array or an antenna of 4 or 5 active elements. And with these elements are very close to each other, but we can put this instrument in a ship, for example, and track and monitorize different areas of the sea, because we can move with the ship. But one of the main problems with this device is the movement of the ship due to the wave, for example, the sea state. We need to compensate for this movement in order to have a good angle information of where the species or the target that we want to localize is. And we do that with, for example, inertial measurement units that count for this or tries to measure the movement of the ship or the vehicle where we install the USBL. And also, usually these devices are quite expensive, are big, power consumption can be quite high, specifically if we want to install this kind of devices in an autonomous vehicle, which is the key point here. So in order to solve this and also I want to mention that this device gives us a measurement of the distance between the device and the target that we want to localize, and also information about the angle, where it is, if it's in the north, in the south, etc. But this kind of angle information can be quite noisy. So the accuracy of this system is less than the accuracy of a long baseline system, because the transponders are more spread in the area and we can improve the accuracy of our predictions or our estimations of the target position. To solve these things, we work with a method that we call range-only target localization, where we only use information about the distance between a surface vehicle, an autonomous surface vehicle, and the target that we want to localize, because the range can be very accurate and we avoid all the errors that we have with the angles. And basically what we need to do in order to estimate the position of the target is to conduct some kind of movement around the target in order to receive distance information at different points, and then apply some triangulation techniques in order to localize the target, as the GPS does in the surface. So there are different techniques in order to find the target, for example, because, well, we have this equation where links all the measurements that we conduct with the position of the target, our own position, and some kind of noise. But this function is nonlinear and can be overdetermined because we can take a lot of measurements around the target. So we need to linearize the function and find ways to solve this equation in order to localize the target. For instance, we could use a closed form least square solution in order. But first of all, we need to linearize using the square of this equation. And then after some approximations, we can apply least square algorithms in order to find the position of the target. Or we could also use some iterative method in order to solve the equation. So we can represent the probability of the target being at position X based on some range measurements with these equations. And then using maximum likelihood, for example, we can try to solve and find the position of the target. But here, one of the main questions for us or for my research was to identify the optimal path that the vehicle should conduct in order to find the better, or in order to find the target more accurately. Because we can conduct some any kind of movement around the target. So what is the best trajectory that we should conduct? In order to solve this optimization problem, if we take a look into the literature, we could use the Fisher information matrix. Here, some publications related to that. So we have the previous equation, and we can build this Fisher information matrix using a series of partial derivatives, in order to find the optimal trajectory to conduct. And if we solve these kind of equations, finally, what the result that we obtain is that all the measurements should conduct around a circumference, and those measurements should be distributed equally around the circumference. And then the final question is, what is this radius? The radius of the circumference should be very close to the target, or should be a big radius. So if we plot this kind of matrix, and we solve this matrix and we plot the solution, we find that more or less during all the cases, if we have a big radius, if we take these measurements around the target far away from the target position, we obtain better results. So the error is lower if we have a bigger circumference radius. So after applying this analytical method, we find the optimal trajectory that the vehicle should conduct around the target in order to better estimate its position. We can run also some simulations in order to collaborate this analytical formula in order to see if agrees or not. And also we can conduct, and we did, some field experiments in order to see how in the reality this methodology works and if this is the optimal path or not in order to localize the target. And for example, we tried to localize an underwater target here in the Monterey Bay in California, which was almost at 2 kilometers deep deployed in the Monterey Bay Canyon. And we use a wave glider, this kind of autonomous vehicle that was equipped with an acoustic modem. And we conducted different circumferences and different other kind of patterns also around this target in order to study this kind of behaviors and to find the optimal trajectory and to correlate with analytical studies that we conducted previously. But what happens if the target is not a static target, but it's a moving target that moves along the time? For example, here we have this simulation where we simulate a target that is moving randomly at different directions, and our vehicle that is simulated with this red cross tries to localize and also track and follow the target that is moving. So the algorithms to triangulate its position are different. We cannot use the least square or some iterative equations. We need to apply other methodologies, for example, the particle filter or some kind of Kalman filter to take into account the movements of this target. And also what happened if the target that we want to localize is quite small, and we cannot use acoustic modems, because with acoustic modems, we have the time of flight, so we can compute the distance between ourselves and the target that we want to localize. Here, in this case, the only electronic device that we can attach in this small species is a pinger, which is a tag, electronic device that transmits periodically a sound, a ping. So with a receiver, we can detect those pings and try to estimate if the species is there or not. But we don't have information about the angle, and we don't have neither information about the distance. So we don't know if it's very close to us or far away. So with this kind of species are more difficult to track and follow them. We did some experiment with the ResNet project a few years ago, where we tried to track and localize these Norway lobsters here in front of Catalan coast in a marine protected area in front of Roses, where we use both techniques. We deployed 4 receivers, so we could use the long baseline system in order to localize 33 target species, but also we tried to localize the species using robotic platforms in order to see how we could use robotic platforms to improve the tracking of the species that are tagged with these small acoustic devices. So here the question is how we can optimize these trajectories in these cases which are more challenging, where we have moving targets or we have very low information regarding the distances or where are the target that we want to track and follow. And to do that was the initial idea, and I applied for a Marie Curie individual fellowship in order to see if we could use reinforcement learning, which is a machine learning technique, in order to find the optimal trajectories that the vehicle should conduct to track underwater targets. And not only a single vehicle, but also we can try to optimize for multiple vehicles that need to collaborate together in order to track not only one target, but also multiple targets, which is very common in reinforcement learning to talk about multi-agent reinforcement learning. But at the beginning, we started with a simple case where we have, again, one vehicle that moves around trying to localize an underwater target. So reinforcement learning works in the following way. Basically, we have an agent that in our case is the vehicle, the surface vehicle that wants to localize the target, and it's represented with its state. That can be its position or velocities and the measurements that conduct into an environment that is a simulated environment that could simulate more realistic or less the underwater environment, and also the position of the target that we want to localize. So at each iteration, we take an action, let's say move to the north or move to the east, and we receive a new state. So it has moved X meters to the north. And also the environment give us or give to the agent a reward. And this agent, the reinforcement learning algorithms, what tries to optimize is not only for the instant reward, but also the sum of the future rewards in order to find the optimal actions that the agent should take at each state. So here, the key function in order to guide the agent through the goal that we want, in this case, to optimize for underwater target localization, is the reward function. And we divided the reward function in 3 different terms. The first one is related to the target prediction error. So if the error of our predictions were low, we give a very high reward to the agent. If the error are quite big, we give to the agent a very low error. Also, we want to stay close to the agent because we want to stay close to the target because we want to not only localize, but also we want to follow the target. So again, if the distance between the target and the agent are low or below a threshold, we give a very good reward. If not, we give a very low reward. And finally, there is a terminal reward, which give some insight into the algorithm that something goes very wrong. And for example, here we give a penalty, a very bad reward, if there exists some collisions between the agent and the target, because We want to avoid this kind of situation. And if the distance between the agent and the target are too close, we just finish the training process at that point, and we reset the environment and we start again. And we give a very bad reward into the agent. So this is the reward function, is a key function in order to guide the agent and find the policy. And then we need also an environment in order to train the algorithms. So we use we modify the OpenAI particle environment in order to use target prediction models and try to optimize for our scenario. So here we can see the blue dot represents the agent that moves in this environment and tries to localize a target that is represented with this black dot. And also we incorporated the target predictions using least square algorithms. And after a few iterations, the algorithm is able to learn the optimal trajectory that it should conduct. And here you can see how the movement that the agent finds and found that is the optimal trajectory in order to reduce the error of the target localization is a circumference around the target, which is the same that we divided analytically. So with this experiment, we corroborate that the reinforcement learning can find the optimal trajectories in these simple scenarios where we have a target that is static, that doesn't move. And also we and we applied this kind of algorithms in order to solve the tracking in a more complex scenarios where we have moving targets. For example, this one in the middle. In this case, the target is not static, the target is moving, and the agent is able to localize and follow the moving target. Okay, we apply different algorithms. In the literature, there are so many reinforcement learning algorithms. And we evaluated all of those algorithms in our scenario that we developed in our environment in order to see how the algorithms are able to find the better policy that will give them the better reward at the end of the episode. So we trained for so many episodes, and we can see that some of the algorithms are better in order to estimate the optimal trajectory than the other ones. And also we take into account and we look how those algorithms are able to reduce the error of the target localization prediction. So again, some of the algorithms are not able to localize quite well the target, but some other algorithms are very fast to localize the target and are able to maintain a good or low error. And after these simulations and these studies, we conducted also a field experiment in Monterey Bay, where we tried to localize an underwater vehicle, an autonomous underwater vehicle with a surface vehicle. And we conduct different trajectories and different tests in order to evaluate and see if this reinforcement learning path following was able to localize and track the underwater targets. And to conclude my talk, now what we are working is into improving the multi-agent reinforcement learning, because we saw that we can use reinforcement learning to track a single target quite successfully. And now what we want to do is to extend to a multi-agent reinforcement learning environment where we have multiple vehicles that need to collaborate between them. So there are different algorithms that are publicly available, but we try to improve them using different architectures in both in the agent network and also in the mixing network in order to improve what is in the state of the art. And for example, here we can see a simulation where 5 agents, which are the red, the circumferences, tries to localize 5 different targets, which are the squares. And in this case, what is interesting is to see that each agent only goes to one of the landmarks or target that we want to localize, because this is a collaborative effort. We don't want that all the agents goes into the only one target, because then we will miss the other one. So they need to spread around and find each one different target. And if we compare the results obtained in this kind of environments, for example, for 3 agents and 3 landmarks, and so on, up to 6 agents and 6 landmarks, we can see that for relatively low or easy scenarios, state-of-the-art algorithms can reach some good results, can coordinate 3 agents to localize 3 different targets. But if we increase the complexity of the scenario, for example, with 6 agents and 6 landmarks, usually the state-of-the-art algorithms are not able to spread and coordinate very well, but our algorithm performs much better. So we published this year this paper in a quite well-known conference in this kind of experiments and scenarios, where we demonstrated in different scenarios how our transform QMix algorithm is able to correctly localize a lot of targets that can easily coordinate a lot of agents to accomplish a single goal, which is localize underwater or localized targets. So thank you very much for your...
Comments, questions? Very nice talk. I have one question. So the idea of this reward thing for the simulations, I think it's very interesting. And for example, it could be also applied for ecosystems or cellular automata or whatever. But so what is the impact or I don't know how to say. So what is the role of the rewards in the simulations? I mean, what consequences it has in the rules of the motions? So how does it work? How do you introduce the reward in the agent-based simulations?
Yeah, as I said, the reward has a huge impact. So because at the end, what the algorithms try to optimize is to get the best reward. So if the reward is different, the behavior of the agent will be very different. So it's quite tricky in order to find the best reward that you need to introduce in order to guide the agent towards the end and to find the kind of results or performance that you want.
But the reward, what is giving to the agent? I mean, if this agent has kind of a reward, what is changing in the properties of this agent? I mean, I don't know.
Because finally, what we have is a neural network, which is a matrix, and you at the entrance or as an input of this matrix, you have the states, and then go through the matrix, and at the end you only have the action that can be move change the speed of the vehicle, for instance. And then you change the speed of the vehicle, you compute the new state, and you get the reward. And then this reward finally is introduced in a loss function that backpropagate to the entrance and change all the weights of the matrix. So when you apply again the same state, all the weight of the matrix has changed, and you will obtain a different action. And it's how you train the algorithm. Basically, what you're trying is to find the best weights of this matrix in order to have a good action at each different state.
Okay, thank you.
More questions, Luis?
I thank you very much for a nice lecture. My question is the following. You had a slide where you were discussing the comparative performance of different optimization algorithms in the network. And there was one that it was marked with a green line, that it was the one converging more quickly to the solution. Okay, this thing. My question is whether this is stable or this changes when the conditions change, when the weather changes or wherever. So, or said in another way, the best algorithm, which I think it would be the last one,
Yes.
It's always the best algorithm, independently on the
Well, yes, usually each algorithm has a lot of parameters that you need to fine tune, and it's quite tricky to fine tune all the parameters. And it depends, I think, from my experience, it depends on the kind of problem that you want to solve. Maybe one algorithm performs better than the other one. So in this scenario, we tried different state-of-the-art algorithms, and we found that the SAC is the best one, and it has some. You can try to explain it also because it has an entropy, and how it predicts the error is different from the other ones, etc. And also it depends on the kind of environment. One of the main issues in this kind of because if everything is in the simulation, but you can fine-tune the algorithms, you can try to find the best one, and that's all. But if you want to apply it into the real environment, it can be quite tricky. And there is this concept that it's called the simulation to reality gap. So sometimes in the simulation works quite well, and then when you apply into the reality, it doesn't work as expected, and it's due to these changes in the real environment. That could be, for example, ocean currents. So how do we reduce this gap? And the scientists and the researchers use different methodologies to reduce this gap. And we here in our simulation, we introduce ocean currents that are one of the main issues in maneuvering an autonomous vehicle on the sea in order to make it stable. And we use random currents with different directions, with different speeds, etc. And also, you train these algorithms a lot of times, so many iterations, in order to find a stable state at the end.
More questions, comments? How many actions could you implement in your model? You mentioned increase the speed or change the direction.
Yeah, we tried only these two, the speed and the action, but at the end, we maintain the speed constant, and we only change the direction. Because also each vehicle perform different and have different action that can be applied. And because we wanted to use a wave glider, that is kind of a surface vehicle that moves with the waves, you cannot change the speed. So the speed is more or less constant based on the waves. So the only action that you really have is the direction that you want to steer the vehicle.
Another question, the reward in the one-dimensional, let's say, it's handmade. I mean, you cook the reward function.
No, yeah, previous.
More backward. This one. It's from your knowledge of the model.
But basically, the parameters that you want to put is based on what you want to obtain. So here we wanted to obtain two things. Basically, is to reduce the error and also to be close to the agent. So based on that, you apply the reward. And there are two kinds of rewards that the researchers used. One is this kind of a step. So you give a 1 if the action is well, and you give 0 if the action is not good. But also there are others that apply this more linear function in the reward. So we did a mixed, but that is the third way. No? You use a mix of both methodologies. And at the end, they are always a terminal reward, because maybe the agent collides with the target, or also the agent goes far away and goes outside of the environment. So you want to avoid these kind of situations. But you take a look on the literature.
Okay, thank you. More questions, comments?
Just more question. What happens in 3D? If the target or the agent, they are moving in 3D, and this would change a lot. It's doable, it's done. I don't know. It's maybe a silly question, but
no, it's a good question. We haven't studied yet the 3D environment. Is in our list of things to do. But usually in how you pilot or use autonomous vehicles, usually is in a 2D. You set a depth and you move in that planar situation. So in a 2D, or if the vehicle moves in the surface is in a 2D, or if the vehicle moves in the seabed, usually is 2D. So if you want to apply these algorithms to control the movement of the vehicles, in a 2D is a good approximation. And then in a 3D is more for the prediction of the target position. So also, again, these equations doesn't take into account the depth, and usually the depth, which will be the 3 dimension, could be measured by a depth sensor, and you can receive this information. Or if the species is a benthic species, you can know a priori what is the bathymetry of the area, and you can estimate more or less this third dimension.
This was my other question. And if the surface in which they move is very complicated, this changes a lot.
Changing how you estimate the position of the target. If the movement are very big, you need to take the measurements far away from the species in order to reduce the error that you obtain with the depth.
Okay, thank you.
Okay, more comments, questions? Yes.
Nice talk. My question is about the devices. The devices, they use ultrasounds, yes? Then they send an ultrasound and come back, right? Then, if the target is moving, probably you can also get a component of the speed, like local effect. Do you use this?
To measure the distance, you don't use exactly ultrasounds like a sonar. What you use is acoustic modems. So they send information using acoustic modulations, and you don't have this Doppler component. But some of these modems take into account the speed of the modems in order to improve the message and the bit rate to exchange the information between modems, but you use some kind of acoustic modulation to compute the time of flight. So it's not exactly like a sonar.